Welcome back to part C of my SlideCast. Now I want to concentrate on fluctuations of heat release, generating acoustic and entropy perturbations. And I start off with this equation here, which you should recognize as, form to express the second law of thermodynamics, or the Clausius inequality. And what you see here is an expression that is often used to describe the strength of entropy waves downstream of a premixed flame with fluctuating heat release rate. So this expression looks very similar to the second law of thermodynamics, and thus we should trust it, shouldn't we? Well, more than 10 years ago, I was invited to review a paper on instability in a premixed combustor test rig. Nice experimental work, a rig with a perfectly premixed flame, so fuel and air were mixed far upstream, no way for acoustics to perturb the equivalence ratio, and then a choked exit. And the experimental work was supplemented by a model, low-order model, network model, which included the generation of entropy waves. And the entropy waves then in the model were argued to play an important role. And my review of that paper was quite short. I said, we have here a premixed flame with constant equivalence ratio. There is no mention of significant heat losses. Also, we should not expect significant effects of non-unity Lewis number. Methane was the fuel. Therefore, this perfectly premixed flame cannot generate equivalence ratio fluctuations. The temperature of the combustion products is always the same, no matter how much heat the flame produces momentarily. There may be fluctuations in heat release rate, overall heat release rate, that result from flame surface area increasing and decreasing, but temperature of the combustion products is the same, so no entropy waves, so the model is not correct and therefore reject. Now, to my surprise, the authors and the editors did not accept this argument, and the paper was published more or less as it was. And so when Lynn Strobio-Chen, a few years later, joined my group, I asked her to work out in detail the differences between a fixed versus a moving heat source. Because from discussion with reviewer and authors, it had become clear to me that this is crucial in this context. And then shortly after Lynn has started her work, this paper by Michael Bauerheim and co-workers appeared in CNF, which discusses a paradox in thermoacoustics, which is that we should use volume conservation for the coupling relation across a compact heat source for zero Mach number, while we should use mass conservation for non-zero Mach numbers. Now that indeed seems paradoxical. A paradox is an apparent contradiction that can be explained though. And reading the paper, it became clear to me that also this paper can be, or this paradox can be resolved by discussing the differences between a moving heat source, like a premixed flame that tries to maintain kinematic balance, and a heat source at rest, like the gauze of a Reiche tube. Now, eventually, our paper appeared, also in CNF. It was not easy to get the paper past the reviewers, not because the math is so terribly complicated, but because the scenarios where we wanted to apply the coupling relation were not easily explained. Nevertheless, Thierry Poisson, who handled the paper as an editor, he wrote me an email after it was published and saying, hey, Now 500 papers go across my desk every year. But this one really stands out because it really resolved this paradox which has bothered him for a long time, it seems. But then, in spite of that praise, I discovered to my dismay that there are still papers that use the wrong model for entropy wave generation, for example. And when discussing with authors, I often hear the argument that, well, this paper by Lindström-Björkén and Sebastian Bomberg is very nice, but it's limited to plane flames, to flat flames only. And my paper is not a flat flame, so the conclusions of this paper are not valid. So I want to continue the discussion now. And let's start off with the difference between a moving flame and a heat source at rest. And following Endowling and also Michael Bauerheim, let's discuss the simple case of a passive flame or a passive heat source that is heat sources that show no fluctuations of heat release rate. Now, for the case of the flame, the demand that it be a passive flame means that it must not change its flame surface area and flame shape. My conclusion would be that, well, in this case, the flame is simply advected back and forth by the flow perturbations. There can be no anchoring because a stiff anchoring of the flame root would generate wrinkles, and the wrinkles would modulate the heat, the flame surface area. So as suggested by the cartoon here on the top left, say an increase of velocity would only displace the flame a little bit downstream without perturbing its heat release rate. But if the flame and the whole arrangement is simply displaced a bit downstream, I can immediately conclude what you see here. The velocity fluctuations on the hot side of the flame is equal to the velocity fluctuations on the cold side of the flame. So this is what Bauerheim would call the volume flow rate conservation. Also from this scenario, you see that there can be no entropy waves downstream of the flame because the temperature of the hot combustion products does not change. Now for the heat source at rest, the situation is a bit more complicated because if total heat release rate is constant, an increase in flow velocity, for example, results in reduced temperature on the hot side. So there will be entropy fluctuations for this case, and it's not easy to relate the velocity on the hot side to the velocity on the cold side because, well, there are also layers of hotter and colder fluid between the heat source and the downstream boundary of my control volume. However, if I consider an infinitesimal control volume, and that is what Bauerheim did, then I can say that this infinitesimally small control volume cannot store any mass. There can be no accumulation because the volume is infinitesimally small. So the mass flow rate at inlet and outlet must be equal. Mass flow rate fluctuations are conserved. Okay. The premix flame does not violate mass conservation because it can accumulate. Now the flame moving downstream, as suggested in the cartoon, would mean more cold stuff inside the control volume. Cold premixture has higher density than the hot combustion products. So with the flame moving downstream, the mass inside my control volume increases. And thus, although the influx of mass and the outflux of mass are not the same, mass conservation is still respected because the arrangement here allows fluctuation of system mass. This is, as I said previously, not the case for the heat source at rest. So this distinction between a heat source at rest and an infinitesimally small volume And a flaming kinematic balance in a compact but not infinitesimally small volume essentially allows to resolve the Bauerheim paradox. Read through this paper with this image in mind and you will see how this can be done. But now let's turn to something more interesting, which is an active compact flame. Now, how do we describe the coupling between upstream and downstream velocity for an active compact flame? And again, we limit the discussion to an ideal premixed flame that is perfectly premixed, no heat loss, no Lewis number effects, a compact volume, no significant fluctuations of density on the hot side or the cold side due to pressure. And we invoke the concept of flame volume, VF, introduced by Blackshear at the 4th Combustion Symposium. What Blackshear does, he says, okay, let's consider the volume of the flame as indicated by the shaded area on this picture here. And they have kinematic conditions, firstly for the mean unperturbed flow state, where I say the volume flux into this control volume, so mean flow speed UC bar times the area A of the duct, must be equal to the volume consumption rate of the flame, so flame speed SF times mean area of the flame. So that this is fairly obvious, right? Volume flow into the system, volume consumption by the flame. We are in steady state, so no accumulation of mass or volume in my flame volume. Now for perturbations, another term comes into the picture. If we allow the flame to move, that is, if we allow that the flame volume, as defined here, can grow, then you see an increase, say, of volume flux into the control volume can be compensated by a fluctuation of flame area or by a fluctuation of flame volume, as shown here. And equivalently, a relation like this holds also for the hot, so the downstream side, downstream of the flame. Only difference is a factor of density ratio comes into the play here because the flame produces more hot volume than it consumes cold premixture, obviously. Okay, if you now subtract the last two equations here, you get a coupling relation between upstream and downstream in terms of the flame surface area fluctuation. And the flame surface area fluctuation we can relate to heat release fluctuations. For an ideal premixed flame, there is a simple proportionality, as you see at the bottom here. And then with some algebraic relation, again we need the mean kinematic condition, we obtain a relation between velocity fluctuations on the hot side and the cold side and the heat release rate fluctuations. Now this result is quite well known. It can be derived by other means, by other paths, so to speak. But this derivation is perhaps the shortest one that I'm familiar with. And importantly, it also corresponds to the results in our CNF paper. So why do a lot of readers think that our paper is limited to flat flames? Well, I have to admit the paper can be misunderstood, and that is perhaps because of this figure. This is our figure 1 in the CNF paper, which seems to show a flat flame. And what one perhaps does quite intuitively, one says, okay, if this is meant to be a flame, then I attach the, I also add conceptually flame speed to this. I have what the equations below suggest, kinematic balance for flow velocities and flame speed and flame movement in the lab flame. For the mean quantities, the flow speed must be equal to the flame speed. The flame movement should be 0. And then before I know it, I arrive at the very boring result that the flame can only be convected back and forth, which we discussed previously. But this is clearly not the scenario we discussed in the paper. we should have used this scenario here, this picture here on the right, because the analysis and the equations we use in the paper correspond to this image. In particular, we define a specific volume consumption rate. This corresponds to the previous slide. Unfortunately, we do not properly define the flame displacement sheet as you would define it, as the area-specific rate of flame volume generation. But if we had done this, we would consistently arrive at relations as shown here. So I think the paper is misunderstood often, because although the math corresponds to the figure on the right, the reader sees figure 1, which you see here on the left, and that is indeed misleading. Also a comment, we should not call this a flame displacement speed, because that is reserved, has other connotations. Okay, now back to entropy. If we again consider the model of Blackshear, but now consider the entropy balance upstream of the downstream of the flame, you see relations as shown here for the cold and the hot side of the flame. In both cases, the rate of flame volume generation appears. And then again, subtracting those two equations from each other, we arrive at the equation shown here on line 3. And this basically balances accumulation of entropy in my control volume with convective transport of entropy into the volume and out of the volume, and then generation of entropy by heat release. And again, introducing area-specific quantities and substituting for the heat of reaction with temperatures and so on and so forth, you arrive at the relation shown here. Again, this is a link between accumulation of entropy inside the volume, convective transport in and out of the volume, and generation of entropy by heat release rate. But the fact that there is generation of entropy inside the volume does not imply that there should be necessarily generation of entropy waves, because the generation term can play with the accumulation term, so to speak. And the first law of thermodynamics tells us across an ideal premixed flame there should be always the same temperature of the hot products, so no entropy waves. And these considerations, of course, also apply to entropy balances in the form shown here now, which you find also in the literature. So the upshot of the discussion is that perhaps we should modify this diagram, which shows that heat release generates entropy wave, and add a qualifier or modification and say, no, it's equivalence ratio that generates entropy waves, but not necessarily and not directly heat release rate. Or maybe we should have an interaction path as follows, that equivalence ratio through heat release in the flame generates entropy waves. So this concludes SlideCast C, and the fourth and last one will discuss linearized Navier-Stokes and linearized reacting flows.